Welcome to this explainer. Today, we're going to dive deep into a pretty incredible engineering reality. We're talking about how massive, continent-spanning power systems manage to survive absolutely catastrophic disruptions. Things like direct lightning strikes.
So what actually happens when 300 million volts of lightning hits a power grid? It's a fascinating question, right? And to answer it properly, we really have to peel back the layers of modern electrical engineering. We're going to build our understanding from the basics to the more advanced levels, looking closely at everything from standard HVDC transmission all the way to complex transient studies. Here's our roadmap for today. We'll be covering 1. The power of HVDC. 2. What are grid faults? 3. Understanding electrical transients. 4. The threat of overvoltage. 5. When lightning strikes. And finally, 6. Defending the grid. All right, let's jump right into Section 1. The power of HVDC, the backbone of the grid.
Now, we all know most of the power flowing into our homes is alternating current, or AC. But when you need to move massive amounts of power across hundreds or even thousands of miles, well, direct current is actually far more economical. A DC line only needs 2 conductors instead of the 3 you'd use for AC. That means less right-of-way, cheaper towers, lower corona loss, the whole shebang. Plus, through advanced converter stations, engineers have this dynamic, full control over the exact amount of power being transmitted.
So high-voltage direct current, or HVDC, is this incredibly efficient technology acting as the true backbone of the modern grid. It really is an engineering marvel. But as we'll see, even the absolute most robust HVDC systems face these hidden threats that can, quite literally, bring the entire network to its knees.
Which brings us to Section 2. What are grid faults when things go wrong? Enter the first real villains of our story, grid faults. A fault is essentially just an abnormal condition. It could be an internal or external disruption, like a short circuit or an arc through a valve, that suddenly causes the electric current to spike or drop dangerously. When a fault happens, that regular, highly controlled flow of power is broken, and it immediately threatens the physical hardware of the grid.
Notice how the exact moment of a short circuit is visualized in these graphs here. You can literally see the bridge voltage just collapsing downward, while the fault current rapidly peaks to maybe 10 or 12 times its normal rated value. If left unchecked, this massive current would instantly melt the incredibly sensitive thyristor valves inside the converter station. To survive this, grid protection systems have to act ridiculously fast. Clearing a fault requires detecting that abnormal current and blocking the gate pulses in less than 20 milliseconds to prevent catastrophic valve damage. Just think about that for a second. The grid has to identify a huge physical failure and shut down the flow of electricity faster than you can even blink. Let's move on to Section 3, Understanding Electrical Transients, the Hidden Shockwaves. So what happens in the immediate aftermath of a disruption? Well, we get what's called an electrical transient. If you've ever heard your home's pipes bang when you slam a faucet shut, that destructive water hammer effect, a transient is a lot like that. In a power grid, a transient is a sudden, momentary variation in voltage, current, or frequency that echoes right through the transmission lines. Now, you might be wondering, why does a transient occur in the first place? These hidden shock waves mostly happen because of sudden changes in the system state. When those safety systems we just talked about suddenly block the converters to clear a fault, it traps all this excess reactive power in the system. Other triggers include sudden load rejection, switching large AC filters, or faults over in the inverter system. Basically, any sudden, massive change in energy flow is going to trigger these ripples. Take a look at these transient voltage waveforms. See those wild, oscillating spikes? That is literal electrical energy echoing back and forth across the DC line right after a fault. It's a totally chaotic environment, and it puts an immense amount of stress on the system's insulation. And those shock waves inevitably lead to our next major topic. Section 4, the threat of overvoltage, pushing the limits. So, to directly answer the question, what is overvoltage? Simply put, it's a condition where the electrical pressure in our system builds up way past its designed upper limit. Think of voltage as the pressure pushing electricity through a wire. Overvoltage is when that pressure gets so impossibly high that it threatens to literally break out of the wires, destroy the physical insulation entirely, and basically vaporize the terminal equipment. Engineers actually classify these dangerous voltage spikes into 3 specific categories based on how fast they hit and how long they stick around. First, we have switching overvoltages. These have slower wavefronts of more than 100 milliseconds. Then there are temporary overvoltages, which might last for a few seconds due to something like load rejection.
And finally, and definitely most dangerously, we have steep front overvoltages. These strike in a fraction of a millisecond, usually between 0.3 and 3 milliseconds. Which brings us nicely to Section 5, when lightning strikes, nature's ultimate test. Without a doubt, the absolute most extreme cause of those dangerous steep front overvoltages comes straight from the sky. When lightning hits an overhead AC or DC transmission line, it injects a massive, incredibly destructive surge right into the system. This surge has a wavefront so steep and so fast that it races at near light speed straight toward the sensitive, multi-million-dollar equipment sitting in the converter stations.
The crucial thing to remember here is that a converter station is essentially a fortress, but it's constantly under siege from all sides. It faces overvoltages originating from the AC side via lightning and switching surges. It faces attacks from the DC side through lightning and ground faults, and it even deals with internal threats like misfires or faults between the valves themselves.
Okay, so we know the threats, but how do we actually protect against them? Let's move to Section 6, Defending the Grid, the Ultimate Armor.
Seriously, how do we build systems that can take a direct lightning strike and just brush it off without plunging a whole city into darkness? Well, the undisputed hero of our story is the modern metal oxide surge arrestor. This is an absolutely brilliant gapless protective device. At normal operating voltages, it acts as a complete insulator. It doesn't let any power leak out, but the instant an overvoltage hits, its properties change entirely.
Look closely at this volt-ampere curve. It perfectly captures the magic of the zinc oxide discs used inside these arrestors. See that steep vertical line? That shows us that at normal voltage, they conduct practically zero current, literally less than a milliampere. But as soon as the voltage crosses a specific protective threshold, the curve flattens out horizontally. In that exact millisecond, the disc becomes highly conductive, safely channeling thousands of amperes of lightning energy away from the sensitive equipment. It's an incredibly elegant, fully automated defense mechanism. First, lightning hits, and the voltage spikes. Second, the zinc oxide instantly becomes highly conductive. Third, the massive surge energy is harmlessly bled off and dissipated straight into the ground. And finally, the exact moment normal voltage returns, the arrestor instantly resets back into an insulator. This all happens so fast we don't even notice a flicker in our lights at home. Which leaves us with a final thought to ponder. We've gone from the basics of HVDC right up to the advanced mechanics of transient overvoltages and surge arrestors. But as global energy demands force us to build grids that stretch even further across harsher environments and facing far more extreme weather, how will our engineering defenses continue to evolve? What new technologies will we need to invent to master the storms of the future and keep the world powered? Thanks for joining me on this explainer, and keep questioning the incredible engineering all around us.